All right. So if you looked at the schedule, you'll notice we're off schedule. That's my fault. Didn't know how to drive good. And so that's cost me $80. So if you ever need to learn how to do insurance, just ask me. And now I know how to deal with insurance. So what we're going to end up doing is this is all going to slide a little bit. And it necessarily will always kind of do that just as we get through the content more slowly. You had a homework. If you can turn that in by the end of today, that'd be great. And then I'll make another homework this weekend. I'll try and grade everything and get everything back to you on Monday. And the next homework will be due the following Monday. The whole full week to work on it. Everyone okay with the last homework? Questions on it? Okay. Caesar's around. You can always send him emails. You can ask him questions in the study room or request to kind of talk to him. We were gonna do a lecture tutorial today, but I don't know how to print, and everyone left, so I couldn't print anything. Yeah, I can't print directly from this computer because apparently that's going to cost money. So, c'est la vie. I should have probably learned. Okay, so what's this? California. Okay, so I was in Tahoe this weekend, and it was fantastic. I went skiing, and it was actually not that bad. Right as I left, the blizzard started coming. They're going to get 4 feet over the next week. Oh my God. Places in Southern California, in the mountains of Southern California, are going to get between 5 and 7 feet. Yeah, it's a lot of snow. And when we talk about the context of atmosphere, that will begin to make a little bit more sense. But in particular, I was looking around at the mountains because I'm a dork, and I was looking at them. I was like, what kind of geology is this? Right? Because we've learned about certain processes. We've learned about volcanism. We've learned about tectonics, we learned about erosion, and we learned about impact cratering. And I was up here, where is it? Right here, okay? And I was kind of like, what causes Lake Tahoe to be so high up? Anyone know? Lake Tahoe is right here. It's not blue thing that. So this is a map of what? This is a map of what state? California. Okay, good. Okay, this is the ocean. And the colors here tell you what kind of rock it is. I do not expect you to know what type of rock that is. That's okay. The lines are fault lines. Okay.
So the volcanic rocks are near the Lake Tahoe area.
Yes. So they were volcanic. And now they're not. So in fact, what ended up happening, if you look at these faults, what is this telling you? What story do fault lines tell you?
There's a movement.
Yeah, movement of
Plates.
Very good. So we have plate tectonics here, and in particular, the fault lines that you see are the movement of several plates. Now, defining something as a plate is not as easy as when you go home tonight and make something on a plate, because that's a discrete object. Here, we're really talking about the fact that pieces of the earth are next to one another, and some of them move and some of them don't. You'll notice here, this is the San Andreas Fault, right? That's the famous one. But there's a lot of other ones too. And in fact, this one kind of goes perpendicular to it. And so you're thinking to yourself, well, is that a plate? No. But there's different sections of rock that have different abilities to deform. Okay? And in fact, we can see the whole history of California right here. Okay, how do I do that? Where is the Sierra Nevadas? Does anyone know what the Sierra Nevadas is? Yeah.
It's like a large mountain range that's kind of like separating Nevada and California around.
Exactly. So in fact, that's this, right? And if you look very carefully here, you see that this is mostly granitic rock. Now you don't know what the word granitic rock is, but essentially this is rock that was melted in our mantle and then it came up. You think to yourself, how did it do that? So what ended up happening is many millions of years ago, there was a different plate that went under California, melted, and then bubbled up as it melted because it was now lighter and it floated back up because it was hot. And it formed a chain of mountains here that were volcanic many millions of years ago, lots of volcanoes, just like now. If you go up to Seattle, you'll see things like Mount Hood, which are active volcanoes. Those are forming for the same reason. Mount St. Helens, the volcano that we saw that absolutely exploded, That's a version of the same phenomenon. Okay. So this plate's going this way, and you'll notice it's not straight. That's scary? No, because rock is bendy, right? It's okay. Everything's gonna be fine, right? Now what happens when this moves? Property prices go down. Very good. We buy houses when the property values go down. Because we've all lived here, it's not scary. But all those people from New York and they finally leave. Yeah, then we buy up all the properties, right? Do a little paint. Cover up the cracks in the foundation. Okay. So we're gonna put all the things that we talked about together today. And as I mentioned before, we won't have a lecture tutorial, but at the start of Monday, we will have one on what we call comparative planetary geology, which is looking through all of the different types of planets. So we've talked about the processes that we've seen, and today we're going to talk more in detail about why this has all happened. Okay? Okay. I want you to have a quick look at this. And based on the features that you see personally, right? What is the why do I have a fifth one? What are they doing there?
Makes it more mysterious.
I think. Oh, cool. All right, I figured it out. Okay, there's 5 answers for everyone. Okay, is this one in the top right one of these 5? Is this one in the top? Don't answer yet. Is this one in the top right one of these 5? Okay.
Well, I have to. What it was at the beginning.
Yeah, I did make it kind of hard. Okay, so what I want you to do is I want you to write down just for yourself. Think about the answer. All right, based on the features you see. Okay, so for this first one. How many people have moon? Raise your hand if moon. Okay, raise your hand if different answer. What's different answer?
I think it's Mercury.
Okay, raise your hand if Mercury. Okay, so about half moon, half Mercury. This one?
Earth.
Raise your hand if Earth. Raise your hand if different answer. What's their difference? I think this is Mercury. Raise your hand if Mercury. Mercury's. Okay. What's this one?
Venus.
Raise your hand if Venus. Raise your hand if different answer. All right, what's your different answer? Oh. What's this one? Mars. Raise your hand if Mars. Okay, raise your hand if different answer. What's your?
I think Mercury.
You think this is Mercury. All right, Mercury is the one that no one really studies Mercury too much, so maybe they don't know what it looks like. So in fact, that is Mercury. What's that one?
It looks like India right there in this complex.
That's the Earth actually, but this is Florida.
Oh, sure.
So the trick that I pulled there is I pulled all the water off and I expanded the topography.
Wow.
I can do whatever I want. I'm teaching the class. What? Yeah, it's kind of the Earth, but I changed it. Right? That's the Earth after all the water gets blown off.
Wait, is Florida that flat for real?
Florida sucks, yeah. Real flat.
It's like super flat.
It's super flat. If you go to Florida and you look around, you can see the whole state.
Holy.
Okay. This one was Venus. Everyone got this one. And this one was the one that was going to give you trouble because I didn't put the color on it. That is in fact Mars. Okay. You can tell that this one's Mars because of these dendritic features. Here, when we compare Mercury to Mars, they're very similar without color. If I don't give you red, you wouldn't know the difference, except for the fact that it looks like erosion happens here, and erosion has never happened on Mercury. Why has erosion never happened on Mercury? There's no atmosphere. We said for erosion to be a significant factor, you needed what kind of things? Water. That was a very good one. Or air can work, and what's another thing that can erode? Ice. Ice is a good form of erosion. In fact, it's what carved the Yosemite Valley. Glaciers move, yeah.
Water and ice is the same thing.
Oh, come on. It's a little bit, I forget it's of water. So for example, you can have CO2 ice, CO2 glaciers, which carve rock. Okay, but you're absolutely right. So fluid, I should say, and if you're in my fluids class, water is a fluid, but also there's other forms of fluid, like for example, liquid nitrogen. Now you don't think about that as critically important here, but maybe when we move out to the outer solar system, we'll see some funny stuff. Okay. This one was obvious. I think everyone got this one. Why is this one so obvious?
That's a lot of scarring.
Scarring, yeah. What about craters? A lot of craters, right? That's it kind of like shows that it's Venus or Earth, right? And then once you see this, you say, well, I don't see any countries that I recognize. Not Earth. Okay. Okay, so we talked a little bit about erosion. Let's finish the discussion. I know it's been 15 years since you took this class last, but Mars in fact has water. When I showed this on the bottom right hand side, I said there's erosional features. Okay, I didn't actually show you last time that there were erosional features on Mars, but here they are. So you hear probably every year that they found water on Mars. That's not wrong, but it's also not helpful as it's like a way to like sell magazines. The thing we're interested in is just to find different forms of water. So we've known for a long time that there's water ice on Mars. There's water vapor in the atmosphere. And sometimes we find different forms of water ice. And that tells us about the history of water on Mars. So in the top left-hand corner, you see what we call dendritic channels. These are channels that form when material is flowing into a larger river. Clearly dried up, right? So this looks like modern Southwest America, right? Desertification. And then this one here is a form of an estuary or something that is like coming from a river and then depositing material here. And what we can do with very cool cameras, we can look at what the composition is. And we see that all of this material in the fan, what's called an alluvial fan, is of the same type. So this river was bringing material with it, and then you have a slight change in the elevation, and it deposits that material on the ground. Then the water disappears, and you're left with the rocks that it brought with it. This one's kind of funny, though. What's this? Okay, here a volcano. Anything else?
Like in a crater.
Volcano in a crater. Where do you see the volcano? Where do you see the crater?
So like the circle, like the previous circle.
This one?
Yeah. It'll be like a crater.
What's that? Bubbles. Okay, I hear bubbles. Yeah.
Is it a crater and like a bunch of wind?
Crater and a bunch of wind. Okay. Okay. So remember that if these are craters, they must be relatively big. Right? So this is like a large structure. Okay. Don't know how many kilometers, but probably maybe hundreds of meters, a kilometer, something like that. And then you have this shape. And that shape reminds you of? Sure, some form of erosion. In fact, if you put a rock here into a stream, you would see water go around it like that. And that's what's happening here. This was a stream or something moving to the right-hand side. There was an impact that punched a hole in it and formed walls. And then that material went behind it. The same thing is true of these. Isn't that weird? So we see that there is like water on the surface, certainly flowing. All of this is evidence of water flowing on Mars. You can see other stuff. There's these fun things called blueberries. This is what happens when rocks tumble. They like smooth out. You've seen the river rocks. And in the bottom right-hand corner is what happens when you have really high resolution imagery. So this is a cliff. And you're seeing icy sort of saline water on the surface of Mars. This is the biggest one in the past like 10 years. Because what you're seeing is basically called a briny solution. Has anyone ever cooked their turkey in brine? Yeah, brine is salt water. So like helps to really retain moisture in the bird. And the same thing is happening here. You can make the mixture of water very, very briny, very salty, then you can change the freezing point enough so that it sort of flows. That's what happens here. It's trapped in the edge of this cave wall. And then as it's exposed to light, it moves out of the edge of the cave wall, goes down like water does, and drains out. Cool, right? And so people want to know, well, okay, bugs? Any bugs that live here? That's our question. That's why we like Mars. Mars looks like it has ancient water, probably did for a long enough time. Did life ever arise on Mars? Is the Nobel Prize winning question, right?
Are you gonna win it?
I'm not smart. Let's go. All right, so here's the 4 processes. These are the ones I'm going to come back to time and time again. Okay. First process, volcanism. Eruption of molten rock onto the surface. We have different types of volcanism. What are the 3 types of volcanism? Slimy volcanism gave you goopy volcanism. This is talking about the viscosity. And it gave you different types of forms that we saw. Shield volcanoes is one of them. Runny volcanoes gave you like a flat plane, right? Like Maria on the moon. And what's the third one? Stratovolcanoes. And what's a good example of that? Mountain Hell exploding violently, right? So the ones that go bang violently, those are stratovolcanoes. Good. Impact cratering, what's that? Meteors, yeah, stuff hitting the surface, deforming the surface. Good example? On the moon, yeah, that's clearly one on the moon. What's an example here on Earth that you can go visit? Yep, which is called? Easiest name. Almost. Meteor crater. Great naming. Okay, tectonics. Yeah, but what does it mean? Good. So very important, right? So notice that she didn't say plates. Right? It's the movement of the surface. That's the correct thing to think about. Because on places like Venus, there isn't necessarily plates that go under one another. It just could be like squishing and moving apart, right? On Mars, we don't think there were plates. Or at least we don't have evidence for that yet. Sometimes it gets uplifted. So here, if you decide to go to Colorado, you can see Boulder. And Boulder has sandstone from the ancient sedimentary floor of an ocean. And as you walk along the mountains here, you're walking backwards in time. It's pretty cool. You can see different fossils from different millions of years. Okay. Finally, erosion. We just talked about that. I'm not going to go over that unless you want to. Okay. Okay. Let's talk about a planet. What are the parts of the planet when we think about composition? 4. Just the planet itself. We'll get to atmosphere later, but yes, that'll be later.
Mantle.
What's that?
Mantle.
Mantle. Good. All right. And then the crust. Okay. So here we have the core, the mantle, and the rocky crust. And they have different densities. Why do they have different densities?
Are they made of like different material?
Yes. Yeah. But why is the highest density stuff in the middle? Heavy sinks. Okay. We're gonna go back to a lot of really simple rules in this class, like hot rises and heavy sinks. Okay. So in fact, this is hottest in the core. Why would that be? Exactly, right? So you have all this mass on top of you, it's crushing you. So it's hottest in the middle, but it's also heaviest in the middle. Okay? Where is it the coolest? Surface. Where we live. Very convenient. You go underneath the surface too far, you melt. We don't like melting. I like the current temperature, even if it could be a little warmer outside, right? Okay. The core is made of metal, mostly iron and nickel. Okay. The mantle is made of what we call silicate rocks. Why are they called silicate? Because there's silicon in them. Yeah. So silicon is an element that's formed inside inside of supernova, gets put into what we make our planets in, and it's less dense, so it sits outside. So for example, if you take, let's say you make a salad dressing tonight, and you put oil, and you put vinegar, and you put a little water in there to dilute it, and some peanut butter, you shake it up, I don't know what you're making, just humor me for a second. And then you sit it down, and you forget about it, you go play video games for 7 hours, and you come back, and they're all separated. I don't know, whatever. Which one is on the top? Well, okay, the lightest one. The lightest one is on the top. And which one is on the bottom? The heaviest, right? And the same thing is happening here. Okay? So this is a process called differentiation. Heavy stuff sinks, lightest stuff floats. So what do you think the crust is made of? The lightest stuff, very good. Okay, so that's what we show. In fact, these low density rocks like granite and basalt are the ones on the top. The composition here between the mantle and the crust, the actual stuff that it's made out is very similar, but the way that it's made is very big. So granite is really great for rock climbing. Why is it really great for rock climbing? It holds its shape well. It's very sturdy. Okay, so I put my hand on it, it's not going to explode. But what's a great example of a type of rock that will explode when you put pressure on it? Sandstone. Yeah, that's what we call choss. So as you put your hand on it, it's really like it's formed by putting layers of old dead skeletons together of bugs. You put your hand on it, it's gone. Okay. Whereas the stuff that's granite is formed in the core, or sorry, in the mantle here, and then it moves back up as it gets warm. Okay. Okay. So that was composition. So let's talk about strength. At the very top, you have this fun word called lithosphere. Oops. This was supposed to show words, but I'll just say them. Lithosphere, when we talk about atmosphere, lithosphere is the place where we live. It's the stone sphere, the exterior of our planet. So everything else below it is just everything else. Mantling core. I'm totally blanking. It'll come when we do this again on Monday. I'll remember what other words are underneath there. How do we know that this is inside of our planet?
That's the magma that explodes out of volcanoes.
Yeah, so that gives us composition. Absolutely. How do we know there's a core?
Magnetic field.
Definitely, we know there's a magnetic field that implies a core. Yeah. How do we know the shape, sign? Has anyone been to the middle?
No.
So despite the fact that like Hollywood would say, oh, the core stops spinning, or we can drill down to the center of the earth, that is not possible. The deepest we've been is like a very small fraction of the surface. We've never gotten down into magmatic chambers in detail. Why? Because lava's hot. We die, right? So in fact, we know about the interior of planets because of we can do this in two ways, and I'll show you earthquakes in a second. Let's use our brains for a second. What if we just wanted to do composition? And I didn't have very much information. Let's say we're thinking about a different planet. And I give you the mass of the planet and how big it is. What could you kind of tell? The density, right? If I add those two things together, I get density. And what can I compare that to? To give us a broad sense of what it might be made of. Okay. A little bit more than periodic table. What would you use in particular? What are some examples of things that you would know that planets could be made of? Yeah, compared to ours, which should be made of rock. Okay, so the word rock has a density. What are other things that are dense that we could compare to? Water. Okay, good. So water is the one I wanted you to get to. What's the density of water?
1 more.
One what? What?
1 gram.
Good. So that's the one we want to have in the back of our mind. Okay. So if we look at water ice, it's less dense than water. Did anyone know that? That's why it floats. So remember that ice is less dense than water, so it floats on top of water. So if you ever need an analogy for what we are doing here, the top of this rock, okay, it's ice on top of water. Okay, ice is cooler. Frozen form is less dense than the melted stuff underneath. Okay, so just imagine next time you're drinking your water with ice, oh, that's me on the top. Okay. All right, rock is approximately 2.7 to 3.7. I'm even gonna change that. Let's say that it's like 3.5. And iron is heavy, very dense. That's why we use it to make important things. And it's about 7.9 grams per cubic centimeter. So let's think about the moon for a second. Okay. The moon has an average density of 3.3 grams per cubic centimeters. Based on this density, we conclude that it must be A, all rock, B, some rock, mostly rock with some iron, C, mostly rock with some water, a mixture of rock, water, and iron, or E, you can't tell, it could be anything. Have a look at that for a second. Let me know when you're ready to vote. Let's vote on 3, 2, 1. Okay, all right, I got a variety here. So let's find someone who doesn't have the same answer as you. Ask them what they got.
Aren't you at her? Wait, maybe just do yeah, that's why I was like.
Yeah.
Well, hold on, don't use any information that you actually know about the moon. Just use information from the table and what this is telling you, right? Don't use color. Don't use like, I see lava on the surface. Okay.
That's there. The iron. Bring it out.
Okay, we ready to revote? Okay, let's revote on 3, 2, 1. Okay, I only have 1s and 2s. All right, who wants to make an argument for their choice? Yeah.
I think the one that just is going off of the average density, it's right in the middle between 2.7 and 9.7, so that means just. Not, there can't be anything denser, that's what the average density is showing, but that's.
Okay.
That's the majority.
Okay. Does everyone agree with that? Does anyone have a different idea? Yeah.
I thought you based off like how Earth's super dense in the middle,
Hmm.
has more dense in the middle of the moon.
Oh, interesting. So maybe it's connected to some of the slides I just showed. Oh, no. God forbid. Huh. Does anyone want to change their answer? Do they have a different thought about that now? Everyone's still happy.
I have a question. So
Okay.
it's an average density, right? So,
Yeah, that's the average density.
I mean.
How do I perform an average density? Yeah, how would I do the average density of a planet? Yeah.
You have to do like a weighted average, right? Based
Oh,
on-
no, that's too smart. I don't want to do that.
If the moon was created from a chunk of the earth, does that mean it formed the same way into?
No, we don't know anything.
Um,
We're being simple, okay? We're being simple folk. And I just want to say something like, how would I form the average density? What I do, like your average density.
take your size,
Good,
take your mass,
good.
and divide the mass by the average size.
Okay, so you find out how tall the person is, and you divide by their mass, assuming they're a cylinder. Okay? That's science, right? So we would say, okay, we have a sphere, and we have the mass and the volume, and then you divide it. And that gives you an average density. Okay. Is that enough? No, why not?
Okay.
What? No, you think it's good? Everyone agrees? What about this thing? It's a globe, so it's like maybe a pound. Very big. Like a foot or something across, 2 feet across, I don't know, no idea. Right? So I could divide those two. And let's say I get something like the density of water. Did I do it? No, what happened?
One number?
It's one number, good, and it doesn't tell me about the distribution of mass. So there's different ways to get to that average density. In fact, here I have an object that is hard, high density, and then inside here, oh, not so much, right? The air in here is basically zero. Oh, shoot. So we can't simply use this one or this one. So I gotta keep you on your toes. I can't always use E as a non-answer. In fact, here we can't tell only by the fact that it can't be all of them, but it very certainly could be a mixture of rock, water, and iron. Because, for example, take the average of iron and water ice. Add this number to this number, 8 plus 1 is 9 divided by 2.
4.5.
4.5. That's pretty close to 3.5. So now if I just add more water than iron, that's gonna balance. Right? So there's tricky ways to make the composition correct. What if I said instead that the average density was 1? You think it was all water?
Almost.
Maybe some water.
Like very little bit of like, say.
Yeah, if I only have these things to build with, it would be really hard. There might be a tiny bit of iron, a tiny bit of rock, but it'd be really hard, right? What if the average density was 18?
You do.
You didn't do thick, okay, iron's not even on there, right? Okay. So in fact, it's not gonna be an item we look at. What would you guess that the average density of Saturn is? It's less than water. Weird. All right, we'll get to that later. So how the hell do you tell the inside? That was this really stupid example, Mateo. I didn't learn anything. I already said it. I said it before we started talking about this. Earthquakes. So this tool that we just talked about is helpful to give us a first approximation of what we're looking at. And in fact, to tell the interior in a lot of detail, you have to do very detailed measurements. So we don't really know a lot about the core of Venus because it's quite hard to land on Venus. And we can't tell what the core looks like. We can tell what the Earth looks like because we live here. And we put seismometers down. We put one right here. We put one right here. And we'll put one in the back of the room. And then something happens in the interior. And we watch it at different locations. And it tells us about the distribution of mass inside of the planet. So for example, if there's an earthquake over here, and there's a detector on the surface here and here, the way that it propagates, right, through the Earth will tell us what it's made of. So if they got the signal at the same time, that'd be very weird. This is the shorter length. Right? So this one gets first, this one gets it, right? There's a bounce sometimes, there's a bending through certain parts, and there's absorption. This is an entire field of science called seismology. Okay. We landed on Mars and we put a seismometer down and we saw Marsquakes.
Oh.
Yeah, no, it's okay. I do it all the time too. But I also say Earth when I'm like talking about it in not earthquake ways. Okay. And so interestingly enough, this is very well studied. And it tells us about the mass distribution to a very high level of detail. Someone also mentioned that there were magnetic fields, and this is correct. So the interior of the planet can be deduced that there's a molten core by the fact that there is a magnetic field. The reason for this is, and I don't know if you've taken E&M, if you have any issues with taking E&M, but there's three things that you need for a magnetic field. You need it to be electrically conductive, you need it to be convecting, and you need it to be rotating. Okay. Electrically conductive just means that it has an ability to bring charge. So either free electrons or free ions. In some cases, this electrically conductive fluid does not have to be a plasma or a magma. What else is an electrically conductive fluid? That might be in a planet, inside of it. Water. So in fact, there are places in the solar system that might have water under their crust. Anyone know that? Europa. Europa. And Europa has salts inside of its water. And the salt inside of that water is electrically conductive. So as we pass by it, we can tell that there's water underneath it that's responding to the magnetic field. Now, it doesn't have its own internal magnetic field, and that is because that fluid is not convective. We haven't talked about convection in detail, but what is it? Someone who's maybe like seen convection before? Oven, so I turn on convection. What does that mean then? Air goes in a circle. Hot goes up, cold goes down. Hot goes up, cold goes down. We'll talk about this in more detail. And then rotation. For reasons that are complicated but fun, you need one fluid to pass by another one to form a magnetic field. So you have all three of these. You know that there's a metal core that's rotating differently than the exterior. Okay. And the word moderately rapid is ambiguous on purpose, because when we say rapid, like compared to what? So for some people, rapid means like Earth-like, one rotation every 24 hours. For some geochemists, they say, no, that's silly. Venus could be considered rapid in a celestial sense, which is one every 360 days or something. Doesn't feel rapid to us, but apparently for some geochemists, that's rapid enough. Okay. Jupiter, those are easy to mix up. Jupiter rotates at about 10 hours. So it's very quickly rotating. And it has one of the largest magnetic fields in the solar system. Okay. Yeah.
Its core is metallic.
Right. So you said the word metallic.
Yeah.
What does that mean?
Like shifted phase.
Right. And it's also able to. Right? Because metals are what electrically conduct. So I stand outside with this rod and it's lightning, about attack, right? 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 Okay. So how does a terrestrial world end up separated into these different parts, a core, a mantle, and a crust? Yeah. When it's a hot liquid, it separates. And what's the process that we're separating by? Differentiation. And in layman's terms, Simple talk. Heavy go down. Heavy go down, light go up. Okay. Differentiation is in fact the right word. Gravity pulls a heavy material to the center. Lighter material rises to the surface, and it separates like this. Okay. Examples in everyday life.
Water and oil.
Water and oil. That's not what this is. I don't know what this is.
Coca-Cola.
No.
Yeah.
Yeah, this is 3 types of cocktails. So this is I think like the clue is on the bottom or something, and then there's like vodka and then cream, and they're separated by density. What?
That's still very
Yeah, so, I mean it's delicious, but it's cool looking, right? And they or maybe I'll show you a video of this on the next one. You can make like a black and tan. Where you put this Guinness. I'll figure this out. Next week, I'll show you some drinks that you can make at home that have these cool separations in density. What's that? Oh yeah, future lab. Just get 17 beers and we mix them. Oh, gotta get rid of this one. Okay, so what parts of the earth are liquid? Is it A, everything under the crust? B, part of the core and the mantle? C, all of the core and part of the mantle? D, just the core? Or E, just the mantle? This is something you'll know from your reading, because I know you're all doing your reading, right, for that extra week. What? Oh, okay, that's the right answer. That's the right answer. I was ahead and then I forgot. Okay. Let me know when you're ready to vote. Vote on 3, 2, 1. Okay, interesting. I got all of the answers. Got all of the answers. Okay. All right. So who liked everything under the crust? Yeah. Why is that? It seems straightforward, right? Yeah. Okay. Who liked part of the core and part of the mantle? Or no one liked it? Anyone like all of the core and part of the mantle? Why is that? Feels good. Okay, what about just the core? No one liked just the core. What about just the mantle? Yeah. Okay, there's some likers for just the mantle. Why is that?
Because the core is the densest part of the planet, like it wouldn't be liquid, it would be like fluid, so it has to be solid and dense.
Okay, I like that. So we're thinking about like density and liquidity, right? So we're gonna get into some weird thoughts because we don't tend to think about rocks at these temperatures, right? Temperatures and pressures you're about to consider are absolutely enormous and they're counterintuitive. So in fact, everything under the surface is not liquid. You like that? Okay, so there's a small section we live on. And it goes, hold on, inner core, outer core, mantle, and crust. The inner core is solid. Then it becomes liquid, and then it becomes solid. It's not fair. That's cheating, Mateo. Okay, so this outer part, actually, so this should go a little bit to the left. This part here, the outer part of the core. And what you're really having to consider here is a very non-intuitive feeling, which is that at very high pressures, things act solid. Whereas when you're at the right combinations of pressures and temperatures, they will act liquid. And this is important because in these different regions, the motion will be quite different. So for example, can a rock convect? No, not as far as I'm aware. Not once it's in solid form. But when it's under enough pressure for long enough time, it'll act sort of goopy, right? So for example, down here, we might have, say, very hot part, and the hot wants to get out. So maybe it uses convection in this section, and then it uses conduction for the rest of it. And we'll talk about what convection is. Questions about this? Okay. All right, how long does it take an object to cool off? Depends on how large it is, good. Anything else? We talk about heat capacity, what does that mean? Ability for something to retain heat, yeah, that's one thing. So imagine that we have all different objects and different heat capacities. Is there any way, for example, let's say you make some macaroni and cheese tonight. Okay, and you got a nice bowl of macaroni and cheese, it's really hot. What do?
Bone.
That's true, but no, that's another thing you do. Okay, you let it cool down. Is there any way to speed up the cooling?
Put it in the fridge.
No. Is there anything I can just do to the macaroni alone? Let's say I have a spoon. You could stir it. What is stirring doing? How?
It's like manual convection.
It's manual convection. You're letting air in, right? You're increasing the volume, or sorry, you're increasing the surface area for heat to escape. Another thing you can do if you don't want to be sitting there, you can just like make a divot in the middle and press the macaroni up against the walls of the bowl. Very weird looking, but it would, no, of course not. I don't make macaroni, but the other one, eat it warm, I don't eat it cold. But if you needed to cool something down, if you increase the surface area, then it'll cool down faster. And in fact, we're going to show this with math. So the heat content depends on the volume. However much heat you have is depending on how much you contract. The heat loss is going to depend on the surface area, where you lose it. Right? Okay. If you want to cool something down, okay, you have the heat content, and you divide it by the loss. Does that intuitively make sense? Did I pull that out of my? Let's think about it in terms of my bank account. Okay? So this is all the money that I have. Okay? And this is the rate that I lose it. So $15 at $5 a day. How many days do I have? 3, right? We can do that math. So the total amount of money that we have in our planet divided by how long we're losing it for, the rate at which we're losing it. And you can see the units are going to work out there. So this is dollars divided by dollars per second or dollars per year, or however you want to do that. And that's going to end up as a time. Does that make sense intuitively?
Yep.
Okay. So the heat loss depends on surface area, and the volume is the heat content. So what does that mean that time to cool is going to scale like? How is that going to increase or decrease with radius? You're going to need to write it down. Where's your pen? Where's your paper?
You wanna?
Okay, thanks. I think that one, you got a little stylus. I forgot this one was cool like that. Like Pop's little pen other than that one. What was the question? Okay, I want you, I've given you information. I said heat content depends on volume. Volume depends on the radius. Let's assume that it's a sphere like this. Okay. The heat loss depends on surface area. This is the surface area of a sphere. What does the time to cool depend on in terms of radius? Ignore any pi's and 4 and any other. Yeah. All right. Heat content. Depends on the volume. The volume is a function of the radius, correct? The heat loss depends on the surface area. The surface area is the volume of the radius. The time to cool something down is the ratio of them. What is the time to cool in terms of the radius? So. Mayhaps, we'll see. Lot of great questions. Let's see. How are we doing? Few more seconds, few more minutes. Want to ask your friend what they got?
I don't know what film you were doing.
Yeah, I actually think I know. Yeah. I think you're right. So. Yeah. Yeah.
It's like,
Yeah, it's. Smaller, bigger.
It's based on you take the volume and divide it by.
But it's more. Yeah.
Yeah.
Okay, how are we doing?
Horrible.
Horrible?
No, but
Down that. Okay, let me ask you a question.
The radius plate.
What cools off faster? A potato or a pea? A pea. Everyone do that or just one person? Who's ready? Okay, we're at Thanksgiving. Again, I'm on the turkey kick. Pea or potato? Which do you eat first?
Potato.
Not in real life.
Oh.
For coolness.
I'm
Pea. Why the pea?
small.
Smaller, and smaller intuitively means cools faster. Why?
That's
Well, that's what?
volume. Math.
Well, mass and volume are, they're both contributing here, right? We just showed that the time to cool scales like radius. So in fact, I show you this. Okay. Time to cool is the volume over the surface area, which is like 4/3 pi r cubed over 4 pi r squared. And I'm gonna say I don't care about that. And these r squareds are gonna cancel with one of those, and I just have something that is proportional to r. Right? Why does it not make sense?
Obvious. The example I thought of in my brain.
Okay, what do you want to, I mean, it's important to like think about. Yeah,
So I have like a lot of this morning, right?
don't make us jealous.
No, I mean, and like, so the models I took out of the value that I had like. Given them.
Yeah.
Stayed former longer, if that makes sense.
Sorry, say that again?
Never mind, I'm sure.
Okay, we can see. Alright, now I'm just thinking. Okay. Does this make sense? So the potato and the pea is the example, assuming lots of things are the same, right? So for example, if I heated up the potato 3 hours ago, and I just heated up the pea, then obviously the potato is gonna cool. So we assume some things, right? So if you, for example, had two planets, they formed at the same time, which is gonna be hotter longer?
The bigger one.
The bigger one. So I have in fact a few planets that we've been talking about, and let's assume that they all form at the same time, even though I've given you no evidence for that. So you have the biggest would be Earth, and then you have Venus, and then you have Mars and Mercury. Which of those is still gonna have heat in its interior? Earth, that's the biggest. I know that one for sure. Is that true? Yeah, thankfully, we have volcanoes and we're still like, living with a magnetic field that we need, I think, in order to live. Which of those won't? Probably Mercury. Anything else? How big is Mars compared to the Earth? You would know up there. Mars is bigger or smaller?
Small.
Smaller by what fraction? 10, 5, 100, a third in size. How much in mass? Do you know? That's okay. That won't necessarily matter. But it's smaller. Imagine it's smaller by a third. How would the time go? A third. So if Mars cooled off in say 3 billion years, how long does that give us? 9 billion years. And we're about 4.5. Uh-oh. It's okay, we're not gonna live that long. Okay. Does that make sense? That process makes sense? Okay. So even though it's super confusing and you all hated it, you get it now. Good. That will be on your homework for sure. Okay. As you increase the, no, that's stupid. Okay. We already did that. Did we do this? Yeah, we did that. So larger objects take longer to cool, right? You can express this as a rate of cooling. So if you just take 1 over that, right? So the cooling rate, what we talked about at the beginning, how quickly does something cool off? And that'll be 1 over R. So smaller things will cool off faster, bigger numbers. Right. Okay. Let's use this again. Now everyone hates it. Lithosphere, what's that again? First anion, the rock sphere. The outer cool hard layer of a planet. Which planet should have the thickest lithosphere in terms of percent of the planet's mantle and crust? Is it A, a large planet? B, a small planet? C, the lithosphere should always be the same percentage of a planet's radius. D, lithosphere thickness does not depend on size. Let me know when you're ready. Vote on 3, 2, 1. At the back. Nothing? Still thinking? Okay. Well, there's enough variety here. I certainly see a lot of 3s, 2s, and 4s. A 1. That's all of the choices. Can you find someone who doesn't have your answer? Convince them of it?
Yeah, I could make it up when we just let you, I can small, faster. And depending on how we take on our head, we can cover how fast they say.
Compared to.
Let's say
Well, it's just let's talk about the pool.
Like the science. The
No,
planets.
I don't think. Because it's faster to move to you. And so it's faster to move the edge.
You guys all agree?
Which means the edge can pick it.
So disagree? Yeah.
Yeah, we can.
All right, let's bring it in, folks. Who wants to make an explanation here? Or defend or ask a question about the question, Mateo, that's poorly posed? Yeah, let's assume that all planets are made of the same stuff.
Okay. The small, okay.
I can.
Yeah, sure, yeah. Oh, yeah. I'm gonna say.
The size is different. Physical size is different, but assume the composition.
No, not.
Anyone like A? So no one fell for A? What about B? Okay, a couple people like B. You want to defend B to the good class? What about C? Who likes C? No one likes C. Two people kind of like C, but you want to defend it? People love D. Everyone is for D, or you just didn't want to answer?
Yeah.
Didn't want to answer, okay. Okay, so let's think about what's going on here. So I said something along the lines of the lithosphere is the cool, hard layer of a planet. And then I said some other stuff earlier about how cooling and heat are related. Right? So we have to use both of those concepts together. So here, the time to cool is proportional to the radius. Right? So cool stuff, like the stuff that's very, very cold, is the stuff that is small. So the pea was cold. The potato was not.
But that's dependent on the medium.
Yes, yeah. So we're gonna assume two things. We're gonna assume all the planets are warmed up at the same time. Just came out the oven. Okay. And we're gonna assume they're all the same type of planet. So the potato and the pea are the same density, it's just small. Okay, that's the assumption. Does that help anyone? No, everyone still hates it. Two? Why two?
Cool fast.
There'd be more cool stuff. Does that make sense? Let's look at these really quickly. In fact, these are the differing planets that we're talking about. And the lithosphere is shown here. Okay. So Earth and Venus, you'll see this is the side, they're pretty close to each other. Right? So Venus is our nearest neighbor. A lot of people, I think of Mars as very similar in size, but it's not. Mars is really small compared to us, right? So the Earth's radius is, I think, something like 5,000 or 6,000 kilometers. And Mars's radius is like 3,400, 3,500, something like that. Okay. And look at the size of the lithosphere. It's huge. What about this one?
Whole thing?
Well, this is the edge of the lithosphere.
Oh, never mind. Sorry.
But it's kind of weird, right? This one maybe don't look at that one. That's Mercury. Something weird happened there. Because it's all core. What? Okay, what about the moon? The moon's the best idea. Right? Moons are the smallest. Look at the size of the lithosphere. It's massive. Right? Because the moon fully cooled off. So we call, by definition, we call the lithosphere the outer cool hard layer of the planet. It's fully rock and it's fully cold. Right? And that is, by definition, the moon all the way until you get to that hard iron mantle core. There is no mantle in the moon. Okay? So it's the small planet has the largest lithosphere. But that leads us to a really big problem. What happened here? Mercury. What happened to Mercury? It's dead. Yeah, it's definitely dead. Yeah, it has a lot of metal. What happened to its mantle?
Got hit too much.
Yeah, that's probably what's ending up. We're gonna come to that when we talk about formation a little bit later, but in fact, we probably think that it had a mantle, and that mantle was ripped off the planet into the sun. And all that's left is the core. Kind of wild, right? It's kind of crazy. So fully differentiated, it was a full-size planet, probably very similar, even maybe larger than Venus or the Earth. If you look at the size of the physical core. So just imagine, it's a huge planet. And there's just leftover junk, and one, just like when we formed the Earth, when we formed the Earth's moon, smashes into the planet, rips off the mantle, and all that goes into the sun.
Literally went into it.
Yeah, it's too close. If you're living around Mercury and you're not on Mercury anymore, you're dead. Okay, you're going into the sun. Okay? People look for what are called what do they call it? Intramercurial asteroids, stuff that lives in between Mercury and the sun. We've never found them, but there's a lot of reason to believe that there's no way that they can exist. You're too small, you're just gonna get pulled into the sun. Isn't that crazy? Okay. All right. So planets have three fundamental properties. Okay. Size. What does size do? Primarily. Gravity. Yes, it has gravity. Good. What else?
Larger radius.
What's that?
Larger radius.
A larger radius means what about a planet?
Bigger.
Takes longer to cool. So the interior of a larger planet is hotter or colder? Hotter. Good. Okay. Can we get volcanoes on a planet whose interior is cold? No. Can we get tectonics on a planet whose interior is cold? No. Good. Okay. So in fact, size of the planet really matters. Larger planets will give us more tectonics, more volcanism, until you get large enough that they're not terrestrial planets anymore. They're not rocky, right? If they're gas giants, then all of this is moot. Okay. What about this other one? Distance from the sun. Did we talk about that at all? Mercury. Okay, so does the distance to the sun affect the interior of our planet? Okay, think about it in this way. We're all having a nice campfire. Okay, you're really cold. What do? You get closer. Does that heat your inside? No, not really. I hope not. You get a fever and you die, right? So it makes you feel better.
Yeah.
But the exterior skin doesn't actually transmit all the way into the interior of your body. Okay, the same thing is true of a planet. We can heat up the exterior a little bit. But we can't put that, like for example, you can't take dead Mars and put it next to Mercury. And then, oh, that additional solar heating, it's not gonna warm up the interior, right? Things dead. Okay. What about that last thing, rotation rate? What does that matter for? What's that, magnetic field? Yeah, exactly, and? Day and nighttime, okay, so even cooler, that's true. Anything else? Talked about it very briefly a week ago, so I, for you for not remembering, more than a week ago, you're gonna have to.
The seasons?
When something spins more quickly, we talked about something called the Coriolis effect, how that turns storms, makes them more violent. We didn't talk about it in detail, but we will talk about it when we talk about atmospheres. Venus spins really slowly. And on the surface, the winds on Venus are non-existent. Totally like still air. Okay. Whereas if you look at the Earth, we rotate relatively rapidly, and we have these wonderful things called hurricanes and tornadoes. And that is from the rotation of the Earth. Is that weird? What about Jupiter? Jupiter rotates even faster. And when we see a picture of Jupiter, we'll see that all it has is. It has no quiescent places on its surface. Quiescent just means lack of storm. Calm. Okay. So these planets have three basic fundamental properties: size, distance, and rotation rate. And we're going to use these to map them to the things that we can see. Okay, the things that we can see are the four geologic processes we talked about. Volcanoes. Someone else? Erosion. Impact cratering. Just one more. Tectonics. These are things we can see. Okay. So if I tell you the size, the mass, and the rotation rate, you can eventually, you'll be an expert. You'll be like, oh, I heard about this new exoplanet today that has this size and it's this far away from its planet star, and it's rotating this fast. And you'll have in your mind a picture of what the surface is like. Present, right? Okay. And the opposite is true. If you look at the surface and you see certain features, that will tell you about the interior, right? You see active volcanism on a planet, you know the interior is hot. It's gotta be hot. Okay? That's where we're going. Okay. So you get 1 minute to ask questions. And you
Can we leave?
Okay, yeah, you these properties we'll use throughout the class, and we'll apply them to different parts of the solar system. The only thing we won't apply them to is gas giants. Oh god. Yes, thank you. Can I get all your homeworks, everything that you want to turn in?
Oh, we're gonna send that.